I'm going to make just a few quick comments about this first example and then move to a more complicated example in preparation for the general theorem. We had the parametrization map which took xy to xyz on the upper hemisphere, and here's the point. This was 1, 2, and that went to 1, 2, 3. And I just want to look at the linear algebra. I want to focus on the linear algebra of these various derivative maps. A, which was d phi, the null space of that, key thing there is that it's as small as possible. It's 0 because this is a parameterization map. It's regular. That's got to be 0. And therefore, the column space of A is as big as possible. And so the dimension of that, which is the rank of A, is 2. And the key thing is that it's as big as possible. The null space of G, everything that's killed by G, well, really crucial thing is that that includes the column space of A. That's another way to say that GA equals 0. Everything that's an output of A is killed by G. Now, what we really want is that these are equal. What's the null space of G? It's everything that's perpendicular to the gradient. Because here's grad G, and the null space of G is just everything that's annihilated, that's sent to 0 by that, and that's going to be everything perpendicular to the gradient. In the picture, it's clear that that's the entire tangent plane, and that's what happens if I take vectors in here and push them forward. I fill out the tangent plane. Why is this true? Well, let's look at the rank of G. The rank of G, it could either be 0 or 1. It was a 1 by 3 matrix. But the key thing was that it was 1. It's as big as possible. And here this was as small as possible. And so this is big. Okay. And let's see how the ranks go together. The rank of G equals 1. It's going from R3 to R1. So the null space of G is going to be two-dimensional. Aha! These are equal. And so this is not just an inclusion, this is an equality. That's crucial. So that's expressing the fact that it's not just that vectors in this tangent plane happen to be killed by G. It's everything that's killed by G. So to be killed by the matrix G, or in other words, be perpendicular to the gradient of little g, is the same thing as being in the right direction, as being tangent to the surface. And that's what we want when we analyze F. We're trying to figure out what does F do only along these directions that are tangent, and that's why the relationship between F and G is so good. I'm going to try and save paper and put it just right here. What do we also know? We also know that, so let's actually do one more thing. The row space of G is what we really are going to be using. The row space of G is everything that's perpendicular to the null space of G. That's one of our fundamental things from the fundamental theorem of linear algebra. And so what does this say? It's equal to, because of this, it's everything perpendicular to the column space of A. Okay. Well, what do we also know? We also know that since FA equals 0, that means a very similar relationship holds, except now it is just an inclusion. It says that the column space of A is inside the null space of F. And now taking perps, that means that the column space of A, perp, is bigger, it reverses this inclusion, than the row space of F. So the row space of F is just all multiples of that one vector, basically the gradient of F. And it says that that's inside the perp of CA. Okay, let's think about that geometrically. It just means that if you are the gradient of F, you should be perpendicular to this level set. Yeah, that makes sense. If you're not perpendicular to the level set of this function, this constraint set, then as you go along the level set, you are going to have a non-zero rate of change in some direction. So that's geometrically pretty clear from in this case anyway. But what is C of A perp? It's just R of G. So that says the row space of F is inside the row space of G. Finally, I'll do it in a new page. This is an unnecessarily complicated way to do it for this case, but this is the crucial way to say it in the later cases. And that just means that f is a linear combination of, well, this one, let's say the gradient of f. The one row of f turned into a vector by transposing it is a linear combination of the rows of g, which of course in this case is just gradient g. So it's a high-tech way of saying that the gradients have to be parallel. Okay, but this is what we're going to see in the other case. Okay, so as we go through the other cases and the general case, you want to come back to this and say, okay, that's really what was going on in this first example, except we would probably never have any motivation to say it exactly that way in such a simple example, if we never went to the more general case. Okay, so example 2, I'm going to pull that out of one of Stewart's examples. So f of x, y, z is the same function, actually. And then I've got two constraints. Let's say g1 of x, y, z is some other plane. So we're on the intersection of a plane and a cylinder. Okay, so let's draw that. Here's the cylinder, and then the plane intersects it. It's not too hard to show, but we don't have to show it in this case, which is nice, that intersects this plane in an ellipse. And we want to know where is this function maximized or minimized. So there's going to be some point, maybe over here, where it's max, over here, where it's min. So, in other words, we're going to say this in a little bit fancier way. We're going to say g, a vector-valued function, a function from R3 to R2, and, well, let's write it as a column vector, is x minus y plus c, x squared plus y squared. And we're going to set that equal to 1, 1. So that's just packaging it up, both constraints into one function. So that's a lot of the time the more pedestrian meaning of when you phrase it in this fancy way of it's the level set of a map to something that's more than just R. You can just say, oh, okay, it says that this ordinary function, just the real numbers, is equal to this number. This ordinary function is equal to this, and it's the intersection of those guys. So the level set of a function with a multivariable output is the intersection of a bunch of ordinary level sets of real valued functions. Okay, so let's see. All right, so let's see. What do we need for this to be a nice set? We definitely, if we're going to use the implicit function theorem to guarantee that this constraint set is nice and that good things will happen when we do derivatives, when we do Lagrange, what do we need? Well, the natural generalization, or it seems like the first thing for the generalization of what we were doing before, is we'd probably want the gradient of g1 not equal to 0, and the gradient of g2 not equal to 0. And that's absolutely true. We need those to be true. But there's one more. What we're going to see to make the Lagrange work, and it's also just to make the implicit function theorem work at all, is that we want them not to be parallel. Let's see, not parallel to g2, to gradient of g2. So the gradients should not be parallel to each other. And that's because if they're parallel, if you have two surfaces, let's say like a sort of a sphere thing here and another sphere thing coming in here, if the gradients are parallel, then the surfaces are touching, and they're parallel at that point. And what do you notice here? I've got a two-dimensional surface and a two-dimensional surface in three-dimensional space. Usually those should intersect in a one-dimensional curve. Here they intersect in only a point. So something is being very weird here. So the cool thing is there's a very nice way to wrap this up into one condition. And not only is that the condition that makes the implicit function theorem work and give the expected answer for what the intersection would be, but also that it makes Lagrange work. So in terms of this, G, what we're really wanting is the derivative map of G at x, y, z. Okay, the derivative map is a matrix whose rows are these guys. We want them to be non-zero, non-parallel vectors. Oh, we want that to have rank 2. Has, or in other words, we want it to be onto. It's going to 2 dimensions, and let's write it out actually. dg is 1 minus 1, 1, 2x, 2y, 0. And we want to make sure that it represents an onto transformation. Or in other words, the column space of G had better be R2. The terminology for this is that the intersection, if you do think about it as the intersection of these two surfaces, one level set of this guy, level set of this guy, they should intersect transversely and not tangentially, or in some even weirder way. So one subtle thing is that we don't actually know what x and y are here. In the first one I cheated and I knew what the x, y, z, I knew what the point was. Let's not worry, let's not try to do that here. Be a little more realistic. So it's a little bit of a concern. What we really need is that no matter what the x and y are, as long as g of x, y, z is equal to 1, 1, we need dg of all those x, y, z's to be onto, even though we don't know exactly which x, y, z it is. So that's it can be a little tricky. It's given that any point on this ellipse, because we don't know yet which point on the ellipse is going to actually turn out to be a constrained critical point when we do Lagrange, which point we're actually interested in. We want all of those points to have this condition. And surprisingly often that's possible to verify. The terminology here is that 1, 1 is what's called a regular value, as opposed to a critical value. A critical value, it's like a critical point, critical number in ordinary one-variable calculus, but it's a little tricky. It's an output such that all inputs that give that output are not, or here it'd be such that one or more inputs that give that output is critical. Regular is that all inputs that lead to this output, all these x, y, z's on the whole ellipse, are give this crucial condition that the derivative matrix is onto. Okay, so let me just set this up in this video. I don't want to make it quite as long as the other video. So we've got dg. Let's call that matrix G. Okay, and we know that it's rank 2, and that's going to be crucial. That's going to make a crucial inequality of sets, subset inclusion, going to turn into an equality, just like in before. Now f, that's going to be df, and that's exactly the same as before, because it's the same function. And again, sometimes we like to think of rows, take rows and think of them as column vectors. There's more sophisticated ways to do that, but it's a good way for this level. That's just the transpose of that guy. If we want G transpose, that might be useful. 1 minus 1, 1, 2x, 2y, 0. Okay. And then what about the parametrization? Okay. Phi of x. So I'm going to choose x here. Remember, the implicit function theorem says that we can choose at whatever point, and again, we're not exactly sure which point we're interested in, but let's just say maybe here. We're thinking the max is around here on the ellipse. Then at that point, there should be one of the variables we can pick, x, y, or z, to be a parameter. Now, there's certainly going to be points where x, for example, fails. If I put the coordinates on here, the x-coordinate is not going to be a good parameter at a point where x maxes out, because then you'd get a graph like this, and you're trying to, like this actually, you can't use x as the domain variable or for a function, for a graph that looks like it. That's not a function, and the derivative goes to infinity as well. But for almost all points, x is a good variable, and for those ones where it's not, you have to use y or z. Okay, so let's hope, and we might have to reorganize the variables if we did this really explicitly, but let's hope that x is a good parameter. Okay, and here's what we actually want to avoid. In the other case, it was pretty easy to actually write down. It was very easy to write down the function as a graph. But here I want to start using more of the full power of the Lagrange idea. I don't want to have to write down the phi1 and phi2. Okay? So there's some functions that parameterize it, except it's some exceptional points where x isn't a good parameter. And I could even, what really matters is just that there's some parameterization. It doesn't even have to be this parameterization that the implicit function theorem gives us that uses one of the variables x, y, z. It could just be there's some way to parameterize it, period. Like phi1 of t, phi2 of t, phi3 of t. There's some way to parameterize it. And the key thing is just that d phi, and we've been calling that matrix A, the derivative matrix of phi, and let's just use x just to be explicit. Okay. Let's go back to that. Just the derivatives of these guys. That's a one-to-one matrix. Okay. And again, that's because we have this curve. Where's our picture? Boy, this is almost as long as that first video. We have this curve. We're just making a nice smooth curve, and it's a regular curve. That the velocity doesn't slow down and stop anywhere, because if velocity slows down and stops, you'll very likely get cusps or corners or nasty behavior like that. Okay, so all we're really going to use is that this is a nice parameterization, and the great thing is we don't need to know anything more about it for this to work. Okay, I'm going to finish up this example in the next video, and then maybe we'll probably be ready to just trot out the general theory, because this example will contain all the crucial stuff.